Okay, thank you very much. Welcome everybody to this second lecture. I'm very happy to be here, and I thank Mathieu for organizing this event and for giving me and my co-authors the opportunity to speak here. So I will continue from where we left off last time. And so before continuing, I will start with a short recap so we all know where we were last time. So I will start with, so what was our goal? So our goal was to define a dependent type theory whose interpretation will give us that types are now infinity categories rather than infinity groupoids. And our approach so far is that we don't start with the syntax yet, but we first axiomatically introduce the syntactic category which the theory should then give rise to. So we first start by introducing this axiomatically, and then the idea is that once we understand these axioms well enough, these are made in a way to be hopefully easily to translate into a syntactic theory. Okay, and so I remind you all of the setup we had. So what we did is we start with the joyal tribe, which means we have some well-behaved notion of isofibrations, path objects, homotopy equivalences, etc. And then, so the way this corresponds to having a dependent type theory, which has which has dependent sums and identity types, but notably, and this is very crucial, we do not have all dependent products, because this is a feature which the category of category doesn't have. And so we have to work with a slightly weaker version of the usual dependent type theory where we don't have access to dependent products. And so the key new thing we're doing is we had this new constant called the interval, and then some long list of axioms describing what this joyal tribe should satisfy. So this was the setup, and let me just remind you briefly about all the axioms which we have seen so far. So I won't spend a lot of time on this, but just briefly. So first we said, okay, this interval is equipped with two distinguished points, 0 and 1. And then these points, they are initial and terminal objects as witnessed by these deformation retracts, which explicitly combinatorially are just given by the minimum and the maximum. Then second, we saw that this gave rise to a monoidal structure, which we called the join, which is given by pushing forward along this map, for which we require that dependent products along this map exist. And so therefore it gives rise to this operator, the join. And then we said that we can therefore define delta n as just an iterated join of the terminal object with itself. And this then gave rise to simplicial operators on our deltas. Then the next thing we required was an internal hom, which we denote fun AB, or with this more shorthand notation B to the A. And using this internal hom, we defined the very important notion of a groupoid. So a groupoid is just any object which sees delta 1 as if it was a point. So the canonical map from X to delta 1 induced by the map to the terminal object is supposed to be an equivalence. And then our theory is made in such a way that if we restrict, if we restrict to the subtribe of groupoids, that then this subtribe, it does have all dependent products. So you can either take this as an axiom right now, or it will in fact follow from an axiom I will introduce a little bit later. And therefore, what we get is that if we restrict to the subtribe of groupoids, it is actually a model of usual HoTT. And so in particular, we have all the theorems of usual HoTT as long as we restrict to groupoids. And then we had a reflection into the groupoids, which is this groupoid core, which is defined as a right adjoint to the inclusion from groupoids. And we demand it to be a more map of tribes. And so in particular, it gives rise to also this this universal property up to equivalence that maps into B from any groupoid is the same as mapping into the groupoid core. And here we use this notation, which maybe wasn't put, which we hadn't explicitly last time, but so I want to make it clear that we are all on the same page about this. So map of AB is just the groupoid core of the internal hom. So it's somehow the mapping space as opposed to the mapping category. And then we had an additional axiom telling us that the groupoid core of our interval is supposed to be just the two endpoints. Then we had what we call the Segal axiom, which basically amounted to saying that simplices inside some X can be written by the usual Segal formula as a homotopy fiber product of one simplices. And then we had this axiom telling us that as full subcategories of the functor category from delta 1 to C, on one hand, we have C, which includes to here via the obvious diagonal. And inside here, we defined the subtype of invertible arrows, which are those which admit both a left and a right inverse as defined by using the Segal conditions to define composition. And then our axiom demanded that this canonical map is an equivalence. So in other words, invertible arrows are the same as identities in this sense. So this can be seen as a sort of completeness condition. And finally, we had this subtype former axiom, which tells us the following. It told us that whenever we have a subgroupoid of the groupoid core of a type, then we can define the induced full subtype, which has a universal property, namely that maps from any other type into this full subtype is the same as giving a map from T to C, such that once you pass to groupoid core, the induced map factors through this given subgroupoid X.
Can you move up?
I'm sorry. Can one not see this?
That's better, but yeah, okay, maybe you have more. Okay.
So on my screen, it goes all the way down, but maybe if on some other people's screen it doesn't, I will try to not use the last few centimeters of the page. Thank you for the hint. Okay. So this was the summary from last time, and now let's continue. I will continue now with giving some of our axioms and then some constructions and consequences.
I would like to make a brief comment, if I may, before you go on.
Yes, of course.
Right in the beginning of your summary there, maybe it's good to go back to it. You said that if you could go down to the beginning of your summary, you said you're working in a category E and you called it the syntactic category. Now, it's okay with me, you can call anything you want, but that's not the usual notion of syntactic category. And I just want to say that for those who are listening so that they're not confused.
Okay.
Usually the syntactic category means we have a system of type theory, and then from the system of type theory, we make a category, we construct a category out of the syntax of the type theory, and we call that the syntactic category of the type theory. But here, there is no underlying type theory. You're starting with an abstract description of a sort of abstract type theory using categorical concepts such as the theory of tribes. And so it's not strictly speaking a syntactic category because there is no underlying syntax. Now, it's an interesting task to try to construct a syntax in such a way that this thing that you have is equivalent to or somehow related to the syntactic category of that syntax. And that task is a different one.
Yes, thank you very much. Thanks for the clarification. Yes, that's exactly how I meant this. So we introduced this category E, which we hope to at some point be the syntactic category of our theory.
Or somehow related to one. Yeah.
Or and as you said, the syntactic theory does not yet exist, or at least only not in full. So what we're doing is we first axiomatically describe this category E of which we wish that it then becomes a syntactic category. And once we have described this category with axioms which are sufficiently somehow, which make sense, then our goal is to translate these axioms into a syntax such that then this E really becomes, as you say, the syntactic category of a syntax. But you're right that what we're doing today, it's not at all about the syntax, it's about the semantics, which of course one then has to find a syntax which gives rise to it. Yes, thank you for clarifying this.
May I just remark one thing?
Yes.
In your description, you said we need this ingredient, which is the interval. But of course, last week, you actually constructed the interval in a certain way, right? Or did you?
No, we demand
No.
that there. No. We don't give give a construction of the interval. It's just we demand that our type E comes equipped with this additional object, which we call delta 1, and it comes equipped with certain structure maps like these ones here. And then we put a bunch of axioms on this. Yes.
Okay.
So this was the recap from last week. So then I will now continue with some more axioms of category theory, which one can now express in this language. And the first thing I want to talk about is the fundamental groupoid of a category. And so what is this? So we define the following. So we have the functor category of functors from C to D. And inside here, we can define the full subtype, which consists of all those functors. Oops, I apologize. This was not supposed to be this thick. We look at all the functors C to D, which factor through the groupoid core. That's what I mean by this notation. And we take the full subcategory, which we can do using the full subtype former. And this full subtype, we denote it like this. So what this is it's all the functors from C to D, which factor through the groupoid core. And now we introduce the following axiom. We introduce the axiom saying that for every type C, there exists a groupoid, which we call pi infinity of C, which is equipped with a map from C to this groupoid, which is universal in the following sense. It's universal in the sense that for all other types D, we have it induces a canonical equivalence of maps out of this fundamental groupoid should be the same as maps from C to D, which factor through the underlying groupoid of D.
I'm tempted to ask you a question now. I'm not sure at the moment if I understand. I mean, could you just explain what this functor, kind of twisted functor, I don't know.
This
from
one?
C to D, yeah. What is it in the case of ordinary categories?
It is just the full subcategory of C to D spanned by those functors which send C into the groupoid core of D. So those functors which invert all arrows of C.
Okay.
This is what it is. It's all the functors which factor through the groupoid core of D.
Okay.
But the point is that natural transformations between them can be non-invertible.
Exactly. So this is, I could have just written this. This would be the functors from C into the groupoid, but this does not have the same natural transformation. By taking the full subcategory of this, as Emily said, that's exactly then all the, we take the full subcategory, so the natural transformation can be non-invertible. Exactly. And so now what we want is that this, that functors, the functor category out of this object pi infinity C into D is the same as this full subcategory of those functors that map through the groupoid core. And so in particular, what this gives us is that this so the core, this symbol tilde is the core, and that one is in fact right adjoint to the inclusion. And what we're defining now is the left adjoint. I apologize, this is a typo, this should be left.
Okay, so intuitively in cat or infinity or quasi-category, this is the functors inverting every arrow, so to speak.
Exactly. And in fact, we will see that we will then put a second axiom which forces this to be exactly that. That will come in a second.
Okay.
And then there's a little lemma. This is just a short computation that if you apply this to delta 1, then you get the terminal object. And this is just a short proof. So whenever you have a groupoid X, then what we have to do is we have to look at functors from this thing here, which by definition is given functors from delta 1 into x. So note, a priori, I would have to put this tilde here, but since x is a groupoid, oh, I apologize, that's not what I meant to do. Since x is a groupoid, this distinction goes away. And then functors from delta 1 into x, that's by definition of being a groupoid, that's the same as functors from 1 into x. And so therefore we see that pi infinity of delta 1 is equal to the terminal object since both are groupoids. So since both are groupoids, it's enough to consider maps out of this into any groupoid, which is what we did. So we see that as we would expect, localizing all arrows in this sense, the fundamental groupoid of delta 1 is the point. Okay, and now we come to the next story, which is about localization, which will then make exactly the connection which Andre suggested. Okay, and so what we do here is the following. So again, we construct a full subcategory of the function type. So again, we have the function type, and we define a full subcategory, which in ordinary category theory should be those functors which invert all arrows in a given class. And so what we do is we take the maps from all the arrows in C, we take a subgroupoid, and now we define the full subtype of those functors from C to D, such that of those functors from C to D, such that if you look at the induced functors on arrows, it will map this collection W, this subgroupoid W, into the invertible arrows on the other side. So this is really the full subcategory of those functors which invert all arrows in D. And now, again, we have an axiom basically stating that this that there's a representing object for this, which is going to be the localization. And so here's the axiom. So the axiom says that if we're given a type C and a subgroupoid, then we have a map from C to, and then we denote this by LW of C, or sometimes with this notation, which again, it's supposed to be the category obtained by inverting, with the universal property that maybe now you would expect. So for all D, we have that functors from this groupoid into D is the same via this map as functors from C to D that invert W. And as a special case, we just write L of C when we're inverting everything. So when W is the class of all arrows. And now note the following, that we have a canonical structure map from, so we have the canonical structure map of the fundamental groupoid, and I claim this induces a map from the fundamental groupoid to, from L of C to the fundamental groupoid. And in order to show this, all I have to show is that if I take this map on the arrows, I have to show that it factors through the invertible ones. But in fact, we saw last week that since this is a groupoid, this map here is actually an equivalence. So the arrows in the groupoid are exactly the same as the invertible ones. And so, of course, this will factor like this, giving therefore rise to this map.
Can you move up your
of course,
page?
yes. Thank you. Yes, I will. And yes, and now the next axiom says that this comparison map is in fact an equivalence. So localizing at all arrows is the same as the fundamental groupoid in the sense before. Okay. Then next, so this was basically the continuation of some of the category theory axioms, and now we're going to start as like a new story, which is, or I mean, it's still a continuation of the same story, but it's a new chapter about fibrations. And before doing that, let me introduce some notation and some motivation if you so want. Okay, so we use the following notation. So when we say objects, which we denote like this, of a type, then what do we mean by this? So by objects, we just mean maps into A out of any arbitrary groupoid, which we then denote like this, which sometimes makes the notation easier. And so how do we think about this? So we think of this as terms of A in context X. So if we think about type theory, then whenever we have a type A, we can think of terms of A, not just in the sort of global context, but also in any context of some other type. And in our type theory, we don't yet know what it means to put something in context of an arbitrary non-groupoidal type, but at least for groupoids, it still makes sense. And this is what we will call an object. So from now on, when I say A is an object in A, or when I use this notation, this is what I mean. It's just a map out of some arbitrary groupoid, amounting to the fact that everything, whenever we say object, what we really mean is that it's supposed to be functorial in the isomorphisms. And yes,
I am tempted to have a quite, maybe this is too quick for, I mean, so context very often can be understood in terms of slicing. So
yes,
your axioms are going to be sort of stable over slicing over groupoids?
Exactly.
Okay.
So they're not at least strictly stable as when slicing over arbitrary types, but they're made in such a way that they're literally true when slicing over groupoids. And so therefore, this is what we mean. So we can always sort of work in a slice over any groupoid. And that's why when I say object, I don't just want really maps out of a point, but really maps out of arbitrary groupoids. But so far, this is really just notation. When I write this, that's what I mean.
Sure.
Okay, and now with this notation, we can do the following construction. So whenever I have two objects of A, I can define the mappings, the Hom space, which we just define as this pullback, where we have this canonical fibration, which is an isofibration, and we pull it back to the to this pair of objects here, and this is what we denote A of AB.
Is your intention in this construction that A and B live in the same context, or is that allowed to vary?
So far, A and B are somehow in the global context. And then whenever you have something in the global context, you can always place it into any other context of any other groupoid. And that's what we mean. But if
Let me ask the same question a different way.
Yes.
Sorry, the way I interpreted the answer you just gave would tell me that sort of the groupoid that's in the lower left-hand corner of the diagram you just drew is terminal. Was that your intention?
It is not necessarily terminal. So I'm using this notation. Whenever I write A in A, I write this set A just to mean the groupoid on which this object X is defined.
Yes. So let me ask. Okay.
Yes.
So is it possible in this construction, is your intention in this construction to allow the case where the groupoid for A is different from the groupoid for B, little a and little b?
Yes, in which case this will be the Cartesian. In which case this will be the Cartesian product of those two. Yes.
Very good.
So this is really just syntactic. Sorry. Yes.
I don't understand the answer to Emily's question. The X equals singleton A suggests to me that you're thinking of X as a terminal object, or is X arbitrary? Or
I'm thinking maybe I'm confusing.
Why don't we take arbitrary generic elements of capital A with an arbitrary domain?
So
X.
the reason is that this will make the statements I want to make true. And so of course we could define an object just as maps out of a singleton, but then I would always have to write instead of, but so, okay, what?
That's what you seem to be doing.
Yes, but so take this as a definition. This symbol for me literally means there's a groupoid X together with a map to A. And the reason I'm writing this is that so I don't always have to say, let X be a groupoid such that this X has a name, so that I can just say, okay, let A be in A, and so that then I can write this. So okay, let me spell this out. So for example, so this is really just X cross Y when A is defined like this, Y is defined like this. This is just a convenient shorthand.
I think the singleton notation is confusing, though, for those who might think you're suggesting you're taking a singleton and picking out the object as a closed element of capital A.
So you can, so maybe this is less confusing. Let me give us this answer. So maybe this is less confusing if you think of, so whenever you have an A, you can view this as, you can put this into context A, which amounts to taking this map.
Context X?
In context X, I apologize. And then the terminal object in this context is X itself.
Yes.
And then a map like this exactly amounts to a map from X to A.
Yes, that's
correct. And so in this context, so basically what I'm doing is I'm just making everything invariant under passing to context in X. So when I use this notation, this X is the terminal object in context X. Maybe I can write it like this. And so it is a single, it is a terminal object in the appropriate context. So yeah, it's really just a notation to indicate that we're working that we're allowed to slice over every arbitrary groupoid.
Well, maybe I like to think of your notations X equals singleton A. That singleton A is just another notation for the codomain of little a, which you
for
may
the domain,
think
exactly.
of
for the domain,
for
yes.
the domain, and which you may think as the context in which A is defined.
That's exactly it. That's exactly it. So this notation singleton A really just is the domain on which A is defined.
It's a bit of a dangerous notation because it's unusual, but that's okay for me. For the time of this talk, sure. Or maybe it's a good notation about.
It's not unusual. It's just that if you do logic, usually you write a deduction symbol. You say in context X, deduction symbol, a small a colon big A. And then you see, instead on the right side of the deduction symbol, you write whatever naive notation you want, and you know it just works. And so we are just doing the same. It's just a matter of psychology here.
Yeah.
So if you think of it like this, then this really just is the terminal object in context X, which is X itself when we think globally, yes. Yes, but I want to, this is really not a crucial point. This is really just notation at this point. And I think there's good reason for this notation, but I'm also, I can also understand that it might be a little bit confusing. So if at some point this causes some trip up, please just ask again, and I'm happy to translate it back into into what's maybe more useful notation, more usual notation. Okay, so now let's talk just a little bit about syntax. So as I said, I don't want to talk, so this talk is mostly about semantics, but I want to motivate what I'm going to do. I'm going to talk just a little bit about syntax. So in this type theory, dependent types, they really correspond to isofibrations. And the big problem of this, or I don't know if it's a problem or a feature, but what we have in this theory, that whenever you have such a dependent type, it does not give rise to a map from A into the universe. So I haven't yet defined what the universe is, but basically this dependent type is not functorial on A the way you expect, because you would, when you have a term in the arrows from A to A prime, then you do not have an induced map from B to A to B to A prime. And this is just the fact that in an isofibrations, you only have the fibers only vary functorially in the isomorphisms, but not in arbitrary maps. And so now what we're trying to do is introduce a new kind of fibration, which corresponds syntactically to a new type kind of dependent, to a new kind of dependent type, which temporarily we will denote like this. So this is only sort of temporary notation. Maybe at some point somebody will find a better one. But this is just to indicate that this is a different type, sorry, a different kind of type which is dependent. And the way we want to think about is that this is a dependent type which really varies fully functorially in A as opposed to only functorially in the isomorphisms. And semantically, these are what are known as Cartesian and co-Cartesian fibrations, respectively. So this plus and minus up here just indicates the variance. One is covariant, one is contravariant. But this is really just a motivation. And now I will come to the definition. I will introduce Cartesian and co-Cartesian fibrations in the sections. The reason I wanted to say this is to come back to what was said earlier, that so we want this category, this tribe we're defining, to come as the syntactic category of some syntax. And while that full syntax isn't yet specified, there are at least some fragments showing what you might attempt to do. And one of those things you might attempt to do is you would introduce two new kinds of dependent types corresponding to Cartesian and co-Cartesian fibrations, respectively. Okay, and so let me now define co-Cartesian and Cartesian fibrations. And first, let me recall what we had from last time. We had the definition of a right deformation retract. I won't read everything, but basically it amounts to a map P and a map S, which is a section. So it satisfies S, and then P is the identity. And then this natural transformation, which essentially exhibits S as a right adjoint, if you want to think categorically, and here are the commutative diagrams that need to hold. And we say that S is a right adjoint section of P. And as a special
yes? P is a reflector in my terminology.
Exactly.
A reflector. Okay.
P is or is it co-reflector? I can never tell the difference, but it's one of those. Yes. S is a right adjoint.
I hope one day you will use this terminology, reflector, rather than right deformation retract, which is a bit awful.
Okay, I don't have a strong opinion about this terminology. I'm very happy to drop it. I like this one though. I like saying that S is a right adjoint section, and I hope that at least
I would call S. It's a bit. I understand. I would call S maybe a reflective subcategory, reflective inclusion.
Yes.
No.
So the reason I will I think so. The reason I like this one is because you will see later that often we will be in the situation where P is given a priori, and therefore the interesting question is whether S exists or not. And so in that case, S really we should think of as a section of the a priori given P. But you will see this in a moment. But I will never use this notation deformation retract again. So I'm happy. If you don't like this, I don't care about it too much.
No. Yeah, sure. Do what you want.
Okay. And as a special case, we say that an object is terminal. So again, object here really just we think of as a map to a groupoid. This is terminal if the corresponding projection has a right, if it is a right adjoint section of this projection. And obviously, then you can do everything dually and define left adjoint sections and initial object. But now I will mostly focus on the right adjoint. Okay, and so now here's the key construction.
Real quick, and that in the definition in green, you ask the homotopy to be fibred over X as well. Is that how I should read it?
Yeah, so X over A is the same data as a section of this map.
I understand that. I'm asking about the two categorical data, the H. Does that need to be over X?
Well, sorry, maybe I'm misunderstanding your question. I mean, by definition, H. So H will be a homotopy, a self-homotopy of this top guy, which will then it will be fibered over X in the sense that it satisfies these two equations.
But Emily, I think I don't know if I understand you rightly. You mean that this is actually like a family of initial object of A. That is an initial object of A over X. Is it what you mean?
Yeah, right. I was just wondering whether we interpret the whole definition over in the slice over X.
The problem could be that X may not be a groupoid here.
X is a groupoid. Yeah, it is. When I say object, I always mean groupoid.
It doesn't matter because you see over X, the interval will be delta 1. Over X, the interval will be delta 1 times X, seen over X through the projection. And then if you do all these formulas relatively to X with fiber products over X, you see it won't matter to do the absolute product with delta 1 or the relative product over X of X times delta 1. It's just associativity of Cartesian product or something.
Yeah, well, sure.
So all I'm here, the only thing I'm really saying is that this map here I can interpret as a map like this, and as a map of this sort, I want it to be a right adjoint section of this projection map. That's really all I'm saying, and this amounts to saying that the fibers are terminal objects.
I'm sorry, I'm lost. Are you now explaining this construction?
No. I was just still answering. I was still just answering what it means to have a section. But I think that's maybe was clarified now. So I will now move on to the construction. No, I haven't yet started with the construction at all. I will do that now.
I mean, just to be clear, the section was not the confusing aspect. It was the adjointness. I was wondering whether it's fiber adjointness or not, but.
Okay, sorry, I totally misunderstood your question. No, I just mean adjointness as maps globally. This map and this map are adjoint just in the sense above, not in any relative sense. But as Denis-Charles says, then you can actually show that this is equivalent.
Okay.
Okay, let me move on. So here's the following construction. So when you start with a map F from B to A, then you have the arrows of B, the arrows of A, and then you have this factorization of B times A to A times A. And now we can form this pullback, and I will use this notation. It's as a sort of lax fiber product. And informally, let me give you a description of this. This is just an informal description of how you can think about this. So this consists of this is somehow an object-wise description if you want. So the objects are triples where you have a B in B, an A in A, and a map from F. Oh, I apologize. This piece here should have been F's. F of B. I apologize. That was just a typo. Maps like this. But the formal definition is this fiber product. This is just sometimes easier to think about, so that's why I write it like this.
This is something called comma-categories.
Exactly. This is the comma category or the lax limit of this arrow. And a special case, we have what is called the slice, which is just a special case when we do this. And here again, this little a is just the domain of, if F is a map from a groupoid, then it corresponds to a map like this, where B will be little a. And then if you do this for that, then that's what I call the slice. Okay. And so now using this, we can come to the key definition of this section, which is the one about Cartesian, or rather co-Cartesian fibrations. So here it goes. So we start with the following. So we start with a map P, and now we consider this forgetful map, which is this one up here, the one from the arrows in B to this comma category. And now we can look at two cases. We can say, if this has a left adjoint section in the sense above, so if it has a section like this, which is left adjoint in the sense that it admits this deformation restrict, then we call P a co-Cartesian fibration.
I see.
And similarly, if this map is an equivalence, then we call P a left fibration. And these are the two key notions in this context.
I see. This is maybe street definition or descriptions of what a Cartesian fibration is. Am I
Exactly.
right?
Exactly. So this is somehow a global, we're producing a global, I will now say in a moment, so this adjoint section, what it does, it picks out a choice of co-Cartesian lifts for all the co-Cartesian lifts that need to be lifting. But it's somehow, we pick a choice. That's what this S does. And so let me explain this just a little bit. What I just said, let me write this down. So what does this mean? So a co-Cartesian fibration how do you think of this? So we have this map from B to A, and the data of an object here, that's the data of a B, together with a map from P of B to some A, which we call alpha. And then this section, which we demand here, so having a co-Cartesian fibration means we have a section here. And what this does, well, it's supposed to map, it's supposed to produce an arrow up top, which we call alpha lower shriek of B. And this whole arrow, if you want, is what the section assigns to this arrow down below. I mean, more precisely, I should really write S of this triple B A alpha. And then if you consider the homotopy of this adjunction and spell out what this exactly means, this will be some sort of this will be exactly the property of co-Cartesian lifts, which maybe let me do it like this. So what this is saying is that whenever you have a map at the top and you project it down, and then you now use the section again to come back. So you use P beta lower shriek of B, then the unit of the adjunction, or rather, sorry, the co-unit of the adjunction will be a map like this, which will express the co-Cartesian property. So this corresponds to a map from SP beta to beta, which is this H of beta. This is how one can unravel what this means concretely. Okay, and what are the key examples we have for this? So the key examples are the following. So first of all, the evaluation at 1 from the arrow category is co-Cartesian. And more generally, so if I scroll up here, if you have here, you evaluate at 1, you can pull back, and this the evaluation from the comma category is also co-Cartesian. And finally, the evaluation from the slice is also co-Cartesian, and in fact even a left fibration. So note that clearly left fibration implies co-Cartesian fibration, because left fibration we're saying is an equivalence, and co-Cartesian fibration we're saying it has a left adjoint section, which is obviously weaker. Okay. And
I'm sorry.
Yes.
On this point, I'm curious about one thing. If you take the global section functor from your tribe to, is it possible to have the value of the global sections of some type A? Does it has maybe a complete Segal space structure or a quasi-category structure or something like that?
Okay, so the global section functor appropriately, yes, this exists. Yeah.
So at the very least, so what you can immediately do is the global section will be a category where objects are homotopy classes of maps from the point.
No,
but
no.
This is not what you meant.
No. I mean the global, not up to homotopy. Just take the global section
so the global,
functors.
you take the Dwyer-Kern localization of the type, and therefore you have a mapping space with value in Kant complexes. And then you can precompose on the left variable with our simplicial object given by the interval and the join. And then they give you a global section functor with value in complete Segal spaces, at least with, I mean, simplicial object in Kant complexes, which are not ready fibrant. So you have maybe to take a ready fibrant replacement. And then it is actually complete Segal.
Yeah.
And then you can translate everything there.
Yeah, good, because then one could possibly use this global section functor to see what happened if you apply it, for example, to a co-cartesian fibrations or something like that, and check that it works well, because one would expect that it takes co-cartesian fibration to co-cartesian fibrations of complete Segal spaces, etc., etc.
Yes.
It's just a comment.
Mm-hmm. Yes, you expect that this global section functor will take adjunctions to adjunctions, and it will also preserve all these constructions of slices and
yes,
and these comma categories and so on. And therefore, since you can define co-Cartesian fibrations in terms of these constructions, it will also preserve those.
Yeah, that's possible. Maybe not only global section, but maybe global, let's say, section from some groupoid or something like that in general.
Yes, you can always slice over groupoids anyway. Yes.
Yeah.
Okay. So then there are some basic lemmas you can prove. I don't want to go into too much detail here because they're not so important, at least for now. So all the things you now expect, you can prove in this context. So for example, you can prove that a co-Cartesian fibration is a left fibration if and only if all its fibers are groupoids. And then now come back to the to what was said also earlier. So we can also define the following. So when P from B to A is co-Cartesian fibration, then we can define is co-cart P as a full subcategory as the essential image of this section, where the essential image you can again define using the full type subtype constructor. And the arrows in this essential image, those we call P co-Cartesian arrows. Okay, and then there's some remarks. So first of all, P is a left fibration if every arrow is P co-Cartesian, and then some things you obviously want for this theory, namely that many of these notions are stable under base change. So left-right deformation, retract, and also left and co-Cartesian fibration are all stable under base change. Okay, so this was the key definition. So we have now the definition of co-Cartesian fibrations. And now I want to come to the next big axiom in the theory. And before I do that, let me give a motivation. So when you start with a co-Cartesian fibration, this again is on the semantic side. And we said that if we think of this in terms of syntax, then we want to think of this as a sort of new type, as a new kind of dependent type. And so now if we look at this notion here, if we look, we have a dependent term like this. Then this notion, if you translate it back to semantics, it really only amounts to the following. It amounts to saying that we have a section defined on the maximal groupoid. And sometimes, of course, what you're actually interested in is actual sections. So really functorial sections, which are fully functorial in A and not just on the isomorphisms of P. And so for this, again, there should be some new kind of judgment on the syntactic side, which maybe we could denote like this, which says that this is really a functorial assignment from terms of A to terms of B of A, in this sense that it's really a section. And now, obviously, in general, you cannot expect that if you have something in this first sense, so something like this, which is only functorial in the isomorphisms, you would in general not expect that you can produce a fully functorial section. But the next axiom is the crucial point, which says that sometimes you actually can. And this is what it says. So it's what we call the assembly principle for terminal sections. And the idea is, if you have a co-Cartesian fibration and you have a section and you have for each point in the base, you have a terminal object in the fiber, then automatically these will assemble to a fully functorial section of your co-Cartesian fibration. So what we're saying is that we assume that we have a co-Cartesian fibration, and we assume that for each A in A, we have an object SA of the fiber, but not just any object, but a terminal object. Then our axiom requires that we can assemble these to a right adjoint section S, which has the computation rule that if you apply S to any given object you start with, it is the section you start with. Okay. So I'll leave that on screen for a moment, because this is really one of the crucial axioms of this theory. What this is saying is that you have an object of each fiber, and you would like to glue these objects to a functorial section. And in general, you cannot do this. But if these objects are all terminal, then you can. And this is a general principle in category theory, that whenever you're talking about something universal, it is often enough to produce universal things somehow pointwise, and by the fact that they're universal, expressed here as being terminal, they will automatically become functorial. So, for example,
I would like to comment on this. I mean, one way to get Cartesian or co-Cartesian fibration is to actually have a reflector, because your co-Cartesian fibration is becoming a reflector because S will be the right adjoint, right?
Yes, exactly.
And therefore, what you're doing here is a kind of characterization, but it's formulated as an axiom of the co-Cartesian fibrations that are obtained from a reflector. Am I right? I mean, not every co-Cartesian fibration is defined from a reflector.
Yes, of course.
Some co-Cartesian fibrations are defined from a reflector, and
yes.
These are exactly those having this property that each fiber has a terminal object.
Exactly, and what we're stating as an axiom is the converse. So note that, so what you're saying is exactly this. So if we already have a right adjoint section, so if we have a reflector, if P is a reflector, so it has a right adjoint section, then it always follows that the fibers have a terminal object given by evaluating this section. And what this axiom is saying is basically the converse, that you can assemble a functorial section just by checking object-wise that you have a terminal object in the fiber. And this really, for me, creates the link between this kind of judgment and this kind of judgment, because you always have something like this, but in general, you cannot go back. But what we're saying here is that as long as you have not just any term, but a terminal term in each fiber, then you can make these functorial.
Mm-hmm.
And
okay.
From this axiom, one can deduce many of these sort of usual principles from category theory, which all amount to this sort of idea that you want to define something functorially, but as long as it's defined in a sufficiently universal way, it's enough to do that pointwise. And so let me start with one example, which is important, which I will need later. So it's the following statement. If we have a morphism of co-Cartesian fibrations, so we have P and P prime. Oh, I apologize. The prime should have gone on this one. Co-Cartesian fibrations. And we assume that F is a morphism of co-Cartesian fibration, which means that it preserves Cartesian arrows. So it sends Cartesian arrows to Cartesian arrows. Then we can detect whether F is an equivalence on fibers. So then F is an equivalence if and only if it is an equivalence for each on the fiber B of A prime to B of A for each A in A. And as a corollary, before I sketch the proof of this theorem, let me give a corollary, which is also important, namely that if you have a co-Cartesian fibration, then the map from P to A is an equivalence if and only if for each A, the corresponding fiber is trivial. And now what I really mean by trivial, because again, because of this confusion because we're working in some arbitrary context, what I really mean is that this map from the fiber down to this domain of the object A is an equivalence. So again, what this is saying is that if you have a co-Cartesian fibration, then you can check that it is an equivalence just by checking that all its fibers are trivial. And yeah, so this corollary follows from the theorem just by applying the theorem to this canonical map. So whenever you have a co-Cartesian fibration, you have a map from that co-Cartesian fibration to the trivial one. And then this condition here exactly says that this map is a fiber-wise equivalence. And so therefore the theorem will give you that it is an equivalence globally. Okay, so.
Sorry, Tashi, just to clarify, so whenever I read for each little a and a, I should read for each object a and a, the sort of generalized elements sense.
Yeah. Yes, by generalized as in map from a groupoid. Yes, that's what you should, exactly what you should read. Yeah. And of course, yeah, so yes. The reason I write it like this is because it's somehow it's closer to the somehow way one would usually write these theorems in terms of elements. Yeah, exactly. Sure. So that's what.
Maybe this is a point. I mean, you know, certainly in many models of infinity one categories, the first theorem is true under the more restrictive condition, where you just consider the elements indexed by the terminal groupoid.
Yeah, if I may comment on that, so you have to imagine that a semantic interpretation could be a category theory in an infinity topos, any one. So that means you would take sheaf on a site. In fact, what you can actually do is that you can restrict to objects which are indexed by an object of the site. And so classically, the absolute case, we take sheaves on a point, and therefore we can restrict to the terminal object. And if you take sheaf on a given general site, you should take elements indexed by any object of your site. And if you work in an arbitrary topos, the canonical site is all objects, and therefore all group points. But and because we are agnostic about the site, it could be in any higher topos. So there is no reason we would expect that the terminal object would be sufficient, because there is no reason to, because it would mean that we claim implicitly that we are working on sheaves on a point, which is restrictive.
Great, thanks.
Thank you for that comment, Denis-Charles. This was very helpful. Exactly. Okay, so let me sketch the proof of this of the theorem. Actually, maybe looking at the time, I actually will skip the proof of this theorem, because otherwise maybe we might not be able to get to all the things I wanted to cover. Yes. Okay. Let me give you the sketch, but I'll omit some of the details. which I was planning to mention, but let me at least give you the rough sketch so you can see how the assembly principle works. So the theorem, the way you do it is the following. So you look at this map from this comma category all the way to the arrow category, and then you take the fiber indexed by the invertible ones. So you take this fiber product here, which I will just spell out informally what its terms are, so it's maybe a bit easier to think about. So these are just triples of this type. So that's what objects in here always are, but it's only those such that when you apply P to B to beta, it is invertible. So it's only those objects in the comma category where the structure morphism becomes invertible once you project down to B. And now you check that Q is co-Cartesian. And I was planning to give some more details about this, but maybe I'll skip those. So this you can just check Q is actually co-Cartesian again. And then what you observe is that what are the fibers of this Q? So if you have a B in little b, and let's denote by A the corresponding image in A, then what's the image, what's the fiber QB? If you unravel what these fibers are, then that's just the same as an object in the slice of B prime of the fiber over this object little b, where this here is just defined to be the fiber product of the slice. Like this, and now you use the fact that the map from B prime A to BA is an equivalence, and so therefore you compute that this is really just the same as BA over B. So I just want to highlight the one crucial point. The crucial point here is that using that fiber-wise we have an equivalence, you can compute the fibers of this co-Cartesian fibration to be just this slice. And this slice always has a terminal object. So you see, this is really just a computation, but that's what it amounts to. Using that you have a fiber-wise equivalence, you can compute the fibers and see that this has a terminal object. And so therefore we can now use the assembly principle. So now what you can now do is you can assemble all these terminal objects coming from here to a right adjoint section of this fibration. Sorry, here maybe I should have said Q is co-Cartesian over B. That's yeah, sorry, I skipped ahead of this. So Q you can project down to B to this thing and then project down further to B, and that's what we want to be co-Cartesian. And so therefore we can now assemble a right adjoint section to this. And using this right adjoint section, you can now get an inverse to your original map as follows. You have from B, you take the section to Q, and then Q you can evaluate to B prime. So remember, Q, look at what the objects of Q are. They're triples, B prime, B, and then some structure map. And then you can just evaluate onto that in that first map, onto that first structure object and get a projection onto B prime. And then you check, and this is a computation you have to then do, that this is indeed an inverse. But you see, what we're doing is we're assembling this inverse by assembling all these local terminal objects which exist in these fibers by the fact that each fiber, that we have equivalence fiber-wise. So this is how you would prove this theorem. Okay,
it's a little bit like the axiom of unique choice, if that means something to anyone.
It does not mean anything to me, but so okay, maybe actually it does. So I think if you're in the special case where all the fibers let me actually think. Actually, okay, no, I don't have a good answer to that. So
In a one
Sorry.
topos, if you have a relation which in the internal logic is functional, for all x there exists a unique y, r x y, then there's a map f from x to y, of which the relation is the graph.
Yes, so this is similar in the sense that if you restrict to the case where the fibers are groupoids,
Yep.
then being a terminal, that groupoid having a terminal object exactly says that it is contractible. And so that's exactly then what you're saying, that if each fiber have a unique object up to contractible choice, then you have a functorial section. Yes, thank you for that comment. That's exactly what this is, just a generalized version where we don't require uniqueness, but only terminality.
Right, this is a fat version of the axiom of, it's the axiom of unique fat choice.
That's one can call it like that, exactly. Thank you. Okay, so now let me quickly talk about adjunctions, because now you can also do a very similar thing. So far we only had adjunct check sections, but you can also define adjunctions in general as follows. So what is an adjunction in this language? So an adjunction, it consists of two functors, f and g, going in opposite directions, and an equivalence as follows. So let me put a diagram on. Oops. So, okay, so what do we have here? So on one hand, we have this comma category, and I've put here the element-wise descriptions because sometimes those are a bit, at least for me, it's easier to think in terms of these. So you have the category of elements A, B together with a map from B to G of A, and you have one of B, A together with a map from F of B to A. And both of these come with a canonical projection to B times A or A times B respectively. And now an adjunction, it really just is the data of an equivalence between these two objects over B times A. So the way you can think about this is that this is really just saying that we have a functorial equivalence between, if you look at what the fibers are of this and this, then you will see that the fiber over A, over little a and little b here, what is the fiber? Well, it's just a space of maps from B to G of A. And similarly on the left, the fibers are precisely these mapping spaces of this form. And so this is just a functorial way to encode the fact that you have what you would usually write down as the adjunction equivalence.
When you say equivalence of Bi-fibration, you mean that the equivalence is both the functors giving you the equivalence is both.
Yeah, sorry. This I don't need this. This what I just mean is that this diagram commutes.
Ah, okay.
Sorry. Bi-fibration is a concept I will introduce in a couple minutes, and originally I had this talk in a different order, and so that's a remnant of this. But this it really just means that this commutes. Sorry for this.
Yeah, and commutes. Do you really mean commutes in the tribe, or commutes up to some kind?
No. I really mean we have an equivalence in
the tribe.
Yes.
A commutative square in the tribe. It's not a commutative square up to a homotopy, so to speak.
No. It is in the slice of the type of A times B.
Okay.
Yes, exactly.
Those maps are isofibrations, so it's a reasonable thing to say. The vertical maps are isofibrations.
There are even bi-fibrations, which I will say in a moment what that means, and this will be then automatically a map of bi-fibrations. That's why it was still there, but that was spoilers. Let's call it spoilers.
So
yes.
Am I understanding correctly that the second condition, the functorial equivalence, is weaker a priori than the first one?
So if you drop the functorial and just say this is true for all objects A and B, then yes, it's weaker, because then it would be saying only object-wise. Okay. But it's only apparently weaker, because as I will say a bit later, these are both bi-fibrations. And actually, if you have a map of bi-fibrations, then it is an equivalence if and only if it's an equivalence fiber-wise. So once you have a map, saying it's enough to say that it induces an equivalence like this.
Okay,
Yes.
thanks.
Yes, but you really need to have the map to begin with. So that's what the functoriality means. So it's not enough to say, it's the same in ordinary category theory, right? It's not enough to say that this set is in bijection to this set somehow independently for every A and B. You want this to be functorial in A and B. And one way to make it precise is by assembling it into a diagram like this.
And the map at the top of the square will be invertible. Is an isomorphisms in the tribe or not?
That is just an equivalence.
Yeah, it's an equivalence, yes, but we can.
It's only an equivalence in the sense of in
the tribe sense. So it's in
the tribe sense.
Yes, exactly.
Okay.
But actually, equivalence in the tribe sense really just means it's equivalent to what you would call invertible as a natural transformation, as in there's, sorry, not enough. What? Okay, equivalence in the tribe sense is equivalent to there's a map the way back together with natural transformation both ways, which a priori are only defined over delta 1, but which then take values in this is invertible. Which are pointwise invertible. Yes.
Of course, in CAT, in the category of categories, this map will be an equivalence if and only if it is actually an isomorphisms of categories.
Yes, so maybe one can even strengthen this and require this to be an actual isomorphism.
Well, I'm saying in CAT, I'm not saying
but maybe
quasi-categories. Yeah, there could be I don't know. Yeah.
Yeah, I'm not sure about this.
In ordinary category, we have isomorphism because the mapping spaces are discrete.
Yeah, sure.
So here we won't have that.
True.
Yes.
True, yeah.
So in quasi-categories, the map could be an equivalence without being an isomorphism, I suppose.
Yeah, and then so from this you can then extract units and co-units. The way you just play around a little bit, and you will get a canonical map from B to the functors from delta 1 to B by you have this canonical inclusion from here, and then you use this equivalence, and then you have the canonical projection there, and this really gives you these two transformations from which you then call the unit and the co-unit. So again, the details here are not so important. This is the sort of thing you can just sit and actually trace through the diagrams. The only point I want to make is that from this notion of adjunction, you really get units and co-units in the sense you expect. And then there's typical lemmas you can prove here. Again, I don't want to go into too much detail. For example, you can prove that adjunctions compose in the sense that if if F and F prime both have an adjoint on the same side, then you can produce an adjoint for the composite. And the thing you would expect, namely that deformation retracts are adjunctions. I mean, we use the word and said deformation retracts are functions with a right adjoint section, and that would not be justified if they weren't actually adjunctions. So yeah, this is also true. You can also prove that they are actually adjunctions in this sense. Okay, and yes?
Of course, I suppose that you can prove that the uniqueness of adjoint, no?
That's, I think, so yeah, okay, let me think about this. So there you have to be a bit careful. Uniqueness as what? Somehow uniqueness of the data of the. So if you have an F, then there should be a unique pair of a G together with this adjunction, making into adjunction. But yeah, this we haven't actually yet worked out, but I would expect this to work. Yes.
Yeah, I hope that's important.
It will be true, but at least we have the list of axioms is not complete yet. And so with a full list, it will be very easy to prove. And it's possible that with the axioms we have seen on so far only maybe we could prove it right away, but
yeah,
with
probably
it would be very, very easy to prove.
yes.
I hope so.
Yeah, it might. So it might be possible with what we already have, but I wouldn't be completely sure about this. But yeah,
I mention it because, of course, it's absolutely basic in category theory. Yeah.
Yes, obviously, this is an important desideratum of the theorem. Yes, I agree with that. Okay, and now you can obviously another big desideratum of adjunction is that you can produce them pointwise. And this also you can prove using the assembly principle. So if you have a map B to A, and you have for each A in A a terminal object in this fiber, then you expect to be able to produce an adjoint G such that this S of A is equal to the triple to the pair G of A and the unit of the adjunction. Co-unit, sorry. Okay, and yes, so how do you prove this using the assembly principle? So first of all, you start with the deformation retract on delta, the one which exhibits 0 as an initial object. So we have 0 in delta 1 as an initial object exhibited by this homotopy called min. And what this one does is it induces left deformation retracts here. So left now, which is, I mean, here it's really just the diagonal, which is like the induced by the projection from delta 1 to a point. And then by pulling back, you also get one here. And very explicitly, let me just tell you what this does on objects so you don't get lost. What this really just does is it sends a B to the triple f of B, f of B, and the identity f of B to f of B. This is somehow the heuristic way of thinking about what this map here does. And now what you look at the following composite adjunction. So you take this adjunction here. That's just this adjunction. And now note that by definition, if you take first I and then evaluate at, sorry, this should be evaluation at 1 now. Oh, this is also a typo. Then you just get back F. That is, so at least from this description, it's clear, and you can also check this. So if you take I and then evaluate at 1, then what you're doing is you're evaluating at this F of B. So that's really just F. And now you use the assembly. So first of all, you notice that this map is co-cartesian. That's something I mentioned earlier. And now, if you look at the assumption of our theorem, what we're saying is that each A, the section, the slice B over A has a terminal object. But these slices are exactly the fibers of this fibration. And so this assumption precisely tells us that by assembly, we get a right adjoint here. Sorry, somebody's speaking, but the audio is very, very low. I don't know if I couldn't hear anything. Or maybe it was just in the background somewhere. Okay, nobody has a, okay. Then,
sorry, I was going to ask actually, how did you define the slices again? Is this a definition or is this a theorem, basically?
Yeah. It's basically a definition or a trivial reformulation of the definition. So you can take the definition that the slice is just the fiber of this, or you can take it to be the fiber of the bifibration delta 1 A to A times A over A comma A times a point. They're all trivial equivalent. So, but yeah, you can just take this as the definition if you want. Yeah, it's always hard to know what it, I mean, when they're so trivially equivalent, it's always difficult to remember, okay, which one was the official definition, which one is just obviously the same. Yeah. Okay, so this is how you can assemble all these terminal objects here into an adjoint, and then using that their junctions compose, you have now produced an adjoint to your original F. Okay. So there are some other things you can prove using this assembly principle, using similar techniques, but maybe it makes sense for me now to move on. You can see that somehow this assembly principle really captures the idea that you can get functoriality out of non-functorial things as long as they were universal enough. That's maybe the slogan I would like you to take home about this, is that typically you cannot get functoriality out of nothing, but or just out of object-wise statements. But if those objects-wise things are universal enough, then you get functoriality, so to say, for free. Okay.
That's what we do in mathematics, right?
Exactly, and this is what this principle really is trying to capture. Okay, so now let me wrap up this section with some more. First of all, there's a minor modification. I won't really go into details. Obviously, you can dualize everything. You can do Cartesian fibrations instead of co-Cartesian, and then again demand an assembly for left adjoint section. You can also just don't do this, and at some point maybe introduce a sort of duality axiom, so that then everything you can just dualize. And then you can also do a thing which I kind of already gave some spoilers before, which namely you can introduce the notion of a bifibration. And so what is a bifibration? A bifibration is a map, is an isofibration from B, now not onto a single type, but onto the product of two types. And it is supposed to satisfy three conditions, or four, I guess. The first two are just that each of the two individual projections, so P0, P0 and P1, they are respectively a Cartesian and a co-Cartesian fibration. So somehow we want to think of this as being contravariant in the first variable and covariant in the second variable. And then there's a sort of compatibility condition saying that if you have an edge in the total space, then you will have that it is P0 co-Cartesian, so it's Cartesian over A0, if and only if it is invertible over the other variable. So it's Cartesian over this, if and only if it's invertible over this, and vice versa. And how you should think of these bifibrations, somehow on a meta level, these really should correspond to functors from A0 up times A1 to groupoids. So the fibers are going to be groupoids, and this is what it corresponds to once you sort of know about the straightening and unstraightening. This is just a remark so you to orient yourselves what this notion is supposed to capture. There's obviously also a slightly more complicated notion, which now I don't want to spell out, where you would here go to categories instead of groupoids, where you would replace this second condition by something a bit more sophisticated. I don't want to do this now because it's not so important, and I will skip that. And here's the key example, which is somehow the mother of all bifibrations, which is the one from delta 1, from the arrows to the two endpoints. And when I say that this is in some sense the most fundamental bifibration, then this can be also made precise in the following. So this is what we maybe would call an axiom of so-called non-dependent directed path induction. There's a little asterisk I will come to in a second. And so what this is saying is that you have this bifibration here, and if you have any other bifibration over A times A, then if you specify a map from A to B, then this will give you a unique map, or unique up to equivalence, maybe I should say, from this functor category, from delta 1A to B. So this you can really think of as path induction, because what this is saying is you want to define something for all paths, where now paths are directed, so they're arrows. And what this is saying is it's enough to do it on the identity arrow, and then you will get a unique map defined on all other arrows. And yeah, so this is what we would call the non-dependent directed.
Why is it non-dependent?
It's non-dependent because this if you think of this as a dependent type, it only depends on the value of the endpoints. And if you think about more general dependent path induction in type theory, you would have B to be already defined over this.
Well, A might be defined over some X. Capital A might be a family of types
course,
over X.
Yeah. That's a separate thing. You could, of course, also have A itself be dependent. But so the non-dependency here I'm referring to is about the fact that B is not dependent over this. But of course, there are many. So this is just a sample version. There are, of course, many different versions of path induction you could try to write down. And this is just the simplest to write down right away. So it's the one I chose. And this also brings me to the little asterisk. So I'm relatively confident we can actually prove this from our other axioms. I just don't want to do that right now. And since I want to use this axiom in the final part of the talk, I just state it as an axiom for now, but one can actually probably deduce this from the rest of the axioms. And in fact, also some other some other dependent versions of path induction. You can also cook up and prove using the other axioms.
Sei dir gegönnt. Is there something special about the map from A to B, or is the triangular head on that arrow just a typo?
The triangular head has no meaning. It's just how I draw arrows. Sorry, I didn't know that this has a special meaning. No, for me, I mean,
it may.
Oh, I apologize. So, I mean, it's just sometimes it's just how I draw arrows. Sometimes, yeah, it has no special meaning. Okay, and yes, and from this, there are some other basic lemmas about Bi-fibrations. So the thing I alluded to earlier, if you have a bifibration, then all its fibers are groupoids. So for every fibers over groupoids are groupoids again. That's what I mean. And as a corollary, you get that what I defined as the mapping spaces are indeed groupoids. So the mapping spaces, remember, were just the fibers over this particular isofibration. And a priori, I didn't say yet that those were groupoids, but in fact, it follows that these are groupoids because this is a bifibration. And finally, you can prove similar theorems as the ones I said before. You can prove again that equivalences of bifibrations can be detected pointwise. So it's an analogous statement as before. If you have a map of bifibrations, so a map of bifibration really just means you have a commutative. You have really just means you have a diagram like this, which commutes, maybe it even just commutes up to homotopy if you want, that doesn't matter in this case. Then this will be an equivalence if and only if it is an equivalence pointwise. Okay.
So could you come back to the definition of bifibration? Sorry.
Yes, I shall come back.
Because I think there is a mix.
Did I make it?
You mixed up something.
Okay.
I think for the last two lines, I think the you want to say that an H beta is Cartesian of a P1 or something like that.
Oh, you're right. Sorry. Yeah, you're right. I did mess that up. Let me just think for a second.
So you have to intertwine P0 and P1 in the last two lines, essentially.
Yes, thank you very much. I did get this. Did get this wrong. Yes. Thank you.
Wait, I liked it better.
No, sorry. Actually, yeah. Sorry. Let me just think about this for a second. I have an arrow.
It's Cartesian for one.
No, it's
projects and ISO on the other. No.
Yeah, no, I think, yeah, I think
it is about you have to take it and either on the other, but you want to characterize is Cartesian edges on relatively to P1. And then this is detected by being invertible through P0.
Sorry, now I'm confused by this. So if I have, okay, let me just think.
Because you see now you're saying that the first axiom, the first line says that P0 is Cartesian, but you don't want to say that it is a right vibration. This is what you are claiming now. It is stronger.
No, it's not. I really think it's right as is.
Yeah, I also think so. If you do it the other way, then what you would be saying, if you do it the other way, then, for example, think of A0 just being a point.
Yeah.
Then what we should get here, then we should really just get a co-Cartesian no, then we should get a right vibration over A1, right? Ah, yeah, you're right. The co-Cartesian edges. Let me think. The co-Cartesian edges should be those.
You have discrete fiber.
There should be all edges should be co-Cartesian. All edges should be co-Cartesian. So it's all of them. No, I think it's correct actually. So if A0 is a point, okay, maybe we can figure this out later. I will just get confused if I think about this. Yes,
it's easy. Yeah.
Also, it's not so important. Yeah, but sorry, maybe I got confused in my head, but I won't get less confused by thinking about it now in the middle of the talk. So I'll just go on and we can maybe discuss this afterwards.
I'm always confused about this, and we should not worry because you can fix it by just looking at the case of cat and
exactly.
Yeah.
Okay, so so let me just see. So how do we want to be doing with time? So we have been basically interspersing all the questions within the talk, which I think is very good. Does that mean I can go until 5, or should I stop earlier?
Mathieu, you're in charge.
So I'm just trying to decide whether I should skip the next section or because there's the
last
part.
No, you should finish. Yeah.
Okay, then I will. Okay, then there's a short interlude section before we come to the big thing at the end, which I will already foreshadow. So just some more definitions you can do here. So you can say that a functor is fully faithful if and only if this square is a homotopy pullback. So what does it mean what does this mean explicitly? So if you look at the fibers, so note these are both bi-fibrations. And so again, checking that a map is a pullback can be done by just checking that it is an equivalence on fibers. And on fibers, if you look at what the fibers are over some point C, C prime here, then the fibers of this vibration on the left, not to be confused with a left vibration, the fibers of these vibrations are exactly the mapping spaces of C, and then the fibers of the other one are exactly the mapping spaces of D. And what we're saying is that this is an equivalence of groupoids. So it's the notion of fully faithful, which you probably would have guessed if you had to come up with it. And now there's a theorem you can prove, which is the one which maybe you would expect, namely that a functor from C to D is an equivalence if and only if it is, first of all, fully faithful, and second of all, it induces a surjection on the zero truncation of the underlying groupoids. So this is what we would call essentially surjective. Okay. So now I want to come and finally define what univalence means in this context. And before I do that, I have to introduce some terminology. And this is these are our relative mapping types. So consider the following. If you have two isofibrations, P and Q, then in general, remember, we do not have dependent products. So we might not be able to form the dependent product along these. But if for some reason this dependent product exists, so if we assume that P admits a dependent product, by which I just mean a right adjoint to pullback, which is a morphism of tribes, if we have this, then we can do the following definition. We can define functor underlined A of BC to be the push forward of the pullback of C viewed over A. So we take this here, this map C over A, we pull it back to B, and we push it forward again. And now if you explicitly compute what this is, so if you compute what does it mean to map into this term, then you can unravel this using the universal property of the dependent product, and then you will see the following. A map from some arbitrary type T into this specific type consists of the following. So it consists, first of all, of a map from T to A. And second of all, you can now pull back these two. And then it consists of the data of a map between these pulled back terms. So, for example, if you think about what are the objects, if you think, for example, T to be a singleton or more generally a groupoid, but then what is this? Then you're just picking out a point in A, and then looking at a map between the fibers over that specific point. So I just want to caution, this is not to be confused with this notation, which is already overloaded as is. We have actually two other things. So we had also something which looked like this, which involved localizations. That's obviously not what this means. But there's also another thing which sometimes is denoted by this, which is just the category of maps over A. And this is really just the global sections of this type underlined functor. So I just want to caution that these are different things which have very similar notation, so it's easy to get them confused.
I am confused.
Good. That's probably, these notations are confusing, yes.
Because it seems to me that what you just explained is something very standard in category theory, that an object B is exponentiable. Here it is actually the object B is over A, right?
Yes,
it's
exactly.
exponentiable. Here it will be exponentiable in the slice category over A. If and only if you can define product over B, which means the right adjoint to the pulling back to B.
Exactly. And I'm just, all I'm doing is I'm just saying, if it is exponentiable in the sense that this P lower star exists, then you can construct the mapping object. I mean, it depends what your definition of exponential is. Maybe for you, the definition of exponential is literally this.
For me, exponentiable means that multiplying by B is exponentiable if Cartesian product with B has a right adjoint.
Exactly, and that's what this one is. Yeah, exactly. And this P lower star is exactly a right adjoint to pullback. That's what I'm saying.
Okay.
And out of this P lower star,
well, it's slightly different because E of B is actually slicing over the category E over B, no?
Yeah, so pullback goes from E of A to E of B. So pullback along P takes something over A and produces something over B. And the P lower, so maybe I should have written this. So this one is P upper star.
The pullback is taking, so the notation E is the tribe, and E of A is the category of iso-fibrations over A.
Exactly. And P upper star takes an isofibration over A to an isofibration over B.
Yeah.
And P lower star is a right adjoint to this.
Okay.
So it takes something over B,
yeah.
and produces something over A.
Okay. I don't want to slow you down, so you can keep up.
I think the confusion is the B and the T in the diagram you just drew should be switched, because you want to pull back Q along. You want to pull back Q over B, not over T, I think.
No, so T is some test object. So, okay, so this definition, it just involves the things appearing in this diagram. So I have this thing, I pull it back, now it lives over B.
Yes, but you haven't done that in the diagram. That's why I'm saying you should swap the B and the T.
Sorry, where maybe I'm misunderstanding. So this notion, are you talking about this notation here, this definition here?
So in the, you unpacked that mapping space for us, and I think you should be mapping into the pullback of Q over B. Instead, you're mapping into the pullback of Q over T.
Yes, but I think this is correct. So if you unravel, so if you map, so you have, if you have T over A, and you map into P lower star, P upper star of C, then this is the same as mapping by a junction. You can pull both adjoints over. So this is the same as mapping P upper star, P lower star of T into C over A. And so now P upper star of T, that's exactly this one. That's exactly T times over A with B. And then the data of this map here, it amounts to the data of this map. So I actually think this is correct, but maybe I'm misunderstanding what the confusion. Maybe we can also talk about this after. So maybe I'm misunderstanding what the remark is.
I'm fine. I think we can figure it out.
Yes. All I want you to take away from this is that the points of this object are points in A together with a map of the corresponding fibers. So a point in A together with a map between the fiber over that point here and the fiber over that point here. That's all this is saying. Okay, and so now comes an important axiom. So here we said if P admits dependent products. And this is something I've been hammering home from the very beginning. Not every P will admit dependent products. However, the following axiom says that dependent products will exist, at least for certain maps, namely for Cartesian and co-Cartesian fibrations. So that means that if we have a co-Cartesian fibration, we can indeed form this new type. So if we have a co-Cartesian fibration P and another co-Cartesian fibration Q, then we can form this new type here. Note that we didn't technically need that Q was co-Cartesian, but I want to look at this setting now where they're both co-Cartesian. So we have this, and we can form this new type of fiber-wise maps between them. And here comes the next, the axiom. And it says that we have a non-full subtype, which we denote by co-cart underline A of BC, which, what does it do? It classifies. So remember, this thing here, it classifies diagrams of this shape. And, rather maps from T to A together with a diagram of this shape. And we want to have a subtype which classifies not all of these, so not all of these fiber-wise maps, but only those where this map up top is a map of co-Cartesian fibrations. So this is a co-Cartesian fibration, this is a co-Cartesian fibration, and we want to have a type which classifies only those maps which preserve the co-Cartesian arrows. So that's what this condition says.
T is a groupoid here or not?
No, T is arbitrary.
T is arbitrary.
Yes. So because if you look up here, this thing here is true. Maybe I should add it explicitly. This is really true for all T, not just for groupoids.
Okay.
So maps from T into this type really are just diagrams like this. So obviously a map from T to A together with an induced diagram on the fibers. And we now just want to restrict to those where this map is preserves co-Cartesian edges.
Okay.
And we want there to exist such a full subtype which classifies these. And again, there's a little asterisk. So what we actually do is we introduce a more general subtype former. So I talked about the full, so we saw a full subtype former last week. And very similarly, one can introduce a more general subtype former, which doesn't just work for full subcategories, but also, for example, for this one, which isn't full, where we're trying to put some condition on the arrows. And using this, you can also deduce. But for today, I will just put this as an axiom straight away without talking about the general type former.
Can we go back to the previous axiom?
Of course.
Where the, okay, one more back. Dependent products of what exist along every Cartesian and co-Cartesian vibration. You want to restrict to which families can you make the dependent product of? Cartesian, co-Cartesian, iso?
Every family. Well, iso obviously, because dependent product is
that's the tribe, yeah.
That's always, but yeah, other than that, always. What I'm saying is that whenever every co-Cartesian vibration P will admit a P lower star, which is right adjoint to pullback. That's what it means to admit dependent products.
Okay. And is there a Beck-Chevalier condition for these? I suppose so.
Sorry, can you say that again?
Usually there's a Beck-Chevalier condition associated with such a axiom. I suppose.
It's automatic.
Yeah, okay.
I mean, it is a consequence because you can check the Beck-Chevalier by looking at the left adjoint of everything.
That's right. Yeah.
So it just amounts to say, of course, you have something to check, which is that the class of co-Cartesian vibration is
closed under composition.
Like that.
That's it, yeah.
Mm-hmm.
Yep. Thanks.
Okay, so now I will come to the very last thing of this talk, which is maybe which is the directed univalence, which is somehow what these axioms have been leading up towards. And let me state the axioms, the axiom first, and then tell you what this means exactly. So first of all, recall that we have a hierarchy of subtribes. So we start with our big tribe E, which we, let's say, call E kappa for some cardinal. And then we have some well-ordered hierarchy of subtribes for every alpha smaller than kappa. Yeah. And now here comes the axiom. So for each of these alphas, we have a type U of alpha, which we call the universe, which lives in the next biggest tribe, E of alpha plus 1. And this is equipped with a univalent co-Cartesian vibration. And I will say in a moment what univalent means. It is equipped with a co-Cartesian vibration which classifies, which is universal amongst co-Cartesian vibrations. So what does this mean? It means that whenever you have, first of all the fibers have the correct size. So whenever you have a map into the universe such that A is of size alpha. So when I write this, the way I should think about this is that A is alpha small for this particular size alpha. So if A is alpha small, then also the fiber of this co-Cartesian vibration is again small. And conversely, you have that every co-Cartesian vibration, if the fibers are small, then there exists a unique pullback which we call the name of P. So you have this co-Cartesian fibration, and it will be uniquely classified by a map to the universe. So this is the usual pullback axiom, the usual universe axiom, that co-Cartesian fibrations, if their fibers are small, they're classified by the universe for types of that size.
But the uniqueness is a bit unusual.
I think we don't ask for uniqueness.
Yeah.
It exists.
It exists.
Yeah, but
there's a canonical choice or something.
But I mean, in concretely, you can make it so that it's unique, right? You can, if you build U tautologically.
Yeah.
No. I think not. It can be unique up to homotopy.
Yeah, exactly. So it's not unique. That is even in practice, it's not.
Okay, sorry. I will erase this then. Sorry, I got confused then. Okay. Okay, so now the key thing, so I mean, this is just sort of the standard axiom saying that you have a universe classifying co-Cartesian fibrations, but now the key thing I haven't told you yet is what this univalent means. And that's going to be the, oops, sorry, it didn't come out right. So I still didn't, okay, whatever.
At the moment, I'm not sure I understand what you mean by a map with fibers in E alpha. I'm not sure. You want to say that something has small fibers or something like that, E alpha.
Yeah, so what I mean is, if I have a co-Cartesian fibration, so if I have a co-Cartesian fibration like this, and I have some T.
Now, where does it live? I mean, it lives in the union with all the tribe?
Yeah, so yeah, it lives in the big tribe. So you start with some map, which is arbitrary.
Okay.
But now you require that every fiber, so whenever you take some T, not necessarily groupoid, some arbitrary T, such that this is small, then you require, if you have a co-Cartesian fibration such that for each small T, the fiber BT is again small.
Okay.
That's what I mean by this one is fiber-wise small.
Okay.
And if it is fiber-wise small, then we demand it to be classified by the universe of small fibrations, by the corresponding universal co-Cartesian fibration.
Okay.
Okay.
So this P alpha, of course, will be small, right?
Yes. Yeah, exactly. Yeah, sorry, maybe I didn't say this.
There exists a small.
Yes, sorry. Fiber-wise small.
Alpha
small. That's the first assertion.
Yeah, sorry. Yeah, I did. This is exactly what it means. Yeah, this condition here. Sorry, I don't know. I got confused. Yeah, this is exactly the statement that it is fiber-wise small. Yes.
Okay.
Thank you. Okay. So now we're almost. So now the only thing I have to tell you is what univalent means, and yeah. So we don't really have time for all the details, but let me. So here's the definition. The definition is a bit, maybe instead of looking at the definition, let's look at the following. So what I'm saying here, it's univalent if there's a certain canonical map, which I won't have time to construct today. Maybe we can do this during the next talk. There's a certain canonical map which induces an equivalence between the functor category in A. So we call a co-Cartesian fibration univalent if the arrows in A are the same as this weird thing here. And let's just unpack what this means explicitly for the universe. Instead of maybe focusing on this, which might be hard to understand, I want to show you what this means explicitly for the universe and why this deserves to be called univalence in that sense. So if we have this universe here, where U is now one of these U alphas, And let's say we are given two small types, C and D. Then by definition, this means that these C and D are going to be classified by two maps to the universe, the name of C and the name of D. And now if you take the fibers of this over this particular thing here, then here is how this looks like. So we now look at the fibers. So by definition, the fibers of this left-hand side, these are just the mapping spaces. So here, remember, A is U. So the functors from delta 1 to A are just the arrows. And then if you take fibers over U times U, then this is just the mapping space in U. And what are the fibers of this thing on the left? If you unravel this using the definitions I gave earlier, you can unravel this. And what is this then? So a fiber of this thing on the left means you have a point in the base, that's our point C, comma D. And then you have to pull back to these two fibrations, which in this specific case are U dot times U and U times U dot. And if you do this, then by definition, you will get C and you will get D. Because on the first variable, the pullback is C, and on the second variable, the pullback is D. And now the data the data of an object in the fiber of this guy is really just the data of this arrow like this. And so if you look at what you have produced, then what we have produced here is really just saying we have the mapping space from C to D. So you see, these types are really just the same as maps from C to D. And so therefore, this equivalence up here on fibers, it really becomes this equivalence. And what is this saying? It's saying that the internal mapping space of the universe, so the HOMS, the mapping space of this type U agrees with the external mapping space of our theory. So the maps, the groupoid of maps from C to D in the theory. That's what univalence is telling us, that arrows in the type are identified with arrows outside the type. Okay, and yeah, I will stop here. Thank you all for your attention, and maybe there are some more questions we can discuss now.
Thank you, Tashi. That's a good punchline. And thank you for the talk. That was I enjoyed it a lot.
I have a question.
It's a good time, but we can take time for questions.
Can I ask a question?
Yes, of course.
Yeah.
So, as I understand, if I understand correctly, in like usual category theory or quasi-category theory, univalence sort of corresponds to having. It should correspond. Practically, it means for me that I have Yoneda Lemma. And my question is: are there other examples of some categories that satisfy this? Other examples of co-cartesian fibrations that are also univalent and that do not correspond to this sort of category of all categories?
I mean, once you have a collection of universe which are univalent, you can look at an arbitrary co-cartesian fibration, and it will be classified by a map to the universe. And then you can prove that being univalent in this in the sense that she described is equivalent to the properties that the classifying map to the universe is fully faithful. So at the end, univalent fibrations are just full subcategories of the category of categories, and there is nothing else. There is no room for.
Thanks.
Yeah, because see what this is saying, what univalence is saying is that the mapping space of your types are given by the external.
It's always given by mapping space by internal mapping space in the category of categories. Yeah.
Well, okay, so this computation was specific for the universe. But yeah, once you know that, yeah. Denis-Charles gave you the answer. There's nothing to add.
And maybe we should add that ordinary univalence, or in ordinary homotopy type theory, is exactly the same statement, except that the universe is only a groupoid, and therefore the mapping space only is the same statement, but you focus on invertible maps. And then you can actually characterize univalent maps in ordinary homotopy type theory as full subcategories of the universe, but the universe is a groupoid. That means it's essentially, say you just look at a groupoid, the full groupoid of all homotopy types given by a collection of homotopy types you like.
Yes, in ordinary type theory, you will be, so this will be the identity type of the groupoid, of the universe. And yes, and this will then, well, I guess you have to, it's not like directly the way I've written it. You have to then first pass to invertible maps. Yeah. Okay, are there any more questions? I mean, is there, somebody writes, you mentioned duality. Are you able to define or axiomatize the opposite type? Yes, but maybe we will talk about this next week. I don't know if Denis-Charles, maybe you can mention this at least briefly, how we deal with the opposite. Yeah, basic.
Yeah. Maybe I just have one question. You said nothing about duality in CAT. You will say something about that next time?
I think so. I don't know exactly. I mean, Denis-Charles, you will,
be
right?
forced to, because I mean the Yoneda Lemma creates duality anyway.
Exactly. So yes,
you see, you will have this univalence. It is straightening and straightening. In fact, it really describes and therefore you will produce. You can produce pre-sheaf, say, and then you can take or covariant functors if you want, usually in the universe, and then you can look at the representable ones, and they will, and it will be something which is equivalent to the opposite of A. So the Yoneda embedding together with univalence creates the opposite, but we'll introduce it but then it creates it only up to equivalence. But so far, we also have included a version of the opposite construction, which is strict, like as an operator. But we are forced to have some opposite category anyway.
Yeah, I don't know if there's any of the confusions we had earlier, which the people expressing them think are pressing enough to maybe go back to. I mean, most of those were probably just some computation things, but if there's something which is particularly pressing, I wouldn't mind looking at it again.
I think it's very good at this point. We are at a good place to stop, and maybe next time when you begin, if you could just summarize what you did today, then people will have a chance, if they have a question left over, to briefly clarify that before we go on.
Yeah, makes sense.
I'm tempted to make an extra comment.
Okay.
If you go back to your definitions of Bi-fibration,
Sorry, wait, too far. Here.
So I wonder if one could take advantage of the fact, because this is a rather involved definition, of the fact that such an object is really just an object over the interval.
What do you mean exactly?
Well, if you have an object, a type over the interval, then you can extract from it a bi-fibration in your sense and conversely.
No, maybe this might be some of the origin of the confusion, because maybe the word bi-fibration gets used in different ways by different people. And I think what you
I'm sorry. Yeah.
What you have in mind, I think, is something different. So do I understand it? Or
no, I think what he means is right. So if you have an isofibration over the interval,
and the fibers
category theory, this corresponds to a bifibration.
Yes. Sorry. Yeah, I understand now what you're saying. Sorry, I misunderstood your original remark. So you're saying if I have 8 over delta 1, and then I define, I have A0, A1 over the 2 points. Then now you're saying that the data of such a bifibration here is the same as the data as of this map to the interval.
Exactly.
Yes, exactly. So yes. So B of A0, A1 will be exactly the fibers of the corresponding.
But I'm not sure we can prove that with the axioms so far.
Yeah, I also not sure.
I think that all this this equivalence of categories between you need a twisted arrow category or something like that, I think, to go back and forth. And the twisted arrow category means you need the Yoneda embedding somewhere. Because you see these bifibrations are also at the end, they are just functors from A0 up times A1 to the universe of groupoids. And so it means you want this univalence kind of thing. You want to go back and forth between some kind of functor, the universe, and so forth. And all this means you need the Yoneda embedding somewhere. And to be honest, I mean, maybe we can do it, but for the moment, I don't know how to deduce the existence of Yoneda embedding from the axioms so far.
Yeah, sure. I'm not saying that this equivalence follow from your axioms, but I'm saying that in the models of quasi-category, it is true. And it's a kind of maybe something that could be exploited in the sense that possibly instead of introducing the notions of isofibration the way you do by listing these 5 conditions, maybe there would be another way to do it by just defining it as an object over the splice category and maybe developing something differently, but I don't know how to do it.
So maybe
the reason we introduce it, sorry, is because we want to have this example that we see that the category of arrows, and actually we want to have a theory enough to develop just the amount of theory to understand this category of arrows.
No, sure. It could be
this one is really given the way we gave essentially.
Yeah,
it's not easy to do that with delta 1.
Yeah, so I'm not saying that you should do it this way, but it's a possibility that maybe could be explored because it would, I don't know. It has to be explored.
In the presence of the other axioms, that will include the existence of the Yoneda embedding, then everything you say will be true, that the bifibration, the way we introduced today, will be equivalent. We produce an equivalent theory, up to homotopy at least, with the theory of fibrations over delta 1. So
not fibration, all maps are over delta 1 would be fine.
Yes. And this would be, it can be deduced from the axioms.
I'm sorry?
It can be deduced from the other axioms.
Yeah. So it's a difference of presentation, I would say.
Yeah. So the reason we start with this one already now is that there are some things we want to already start doing, like for example, talking about fully faithful maps or all these sort of basic lemmas. It's very useful to have this notion.
Okay.
Yes. And then later, as Denis-Charles says, once we have the other axiom which imply the Yoneda embedding, then we can see that it's actually equivalent to the other definition you gave.
Yeah. By the way, in your example downstairs, functions delta 1, a, etc. In this model, then this is just crossing a with delta 1. I mean, if you cross A with delta 1, you get that A cross delta 1 is over delta 1, and that's it. That's the bi-fibration you're looking at.
Mhm.
So look, I like very much what you're doing. I like it very much. I'm just
Thank you.
proposing that maybe something could be presented different, slightly different way, but maybe not. I don't know. I don't know. Yeah,
Yeah.
it's just
Thank
a
you for
comment.
the,
Yeah.
Thank you for the comment.
Okay, thank you, everyone. We'll see you next week for the last talk.
See you. Thank you.
Thank you.